Hey everyone, Houston Math Prep here. We are doing our introductory video on how to integrate by trig substitution, the method of trig substitution. So when you start out doing integration, antiderivatives, you learn a bunch of definitions for antiderivatives. I've got a few here. All of them would be worked slightly differently. The first one, integral dx over 1 plus x squared. This is just a definition. When we do the antiderivative of this, we should just get that this is the inverse tangent of x plus some constant. After we've learned some definitions and antiderivatives, then we go on to learn a method of substitution. So if we look at this next one, integral 2x over 1 plus x squared dx, then that would use the idea of u substitution, where we simply let u equal the bottom and du is the top and use some sort of a log rule to complete that. The next one, later on, we learn something about integrating by parts. It's kind of a product rule for integrals. So this next one, 1 plus x squared quantity times e to the x dx, would be integration by parts. And it's pretty typical that as you're learning to choose methods for integration, this is kind of how you would go through your mental checklist. You would first say, is it some sort of definition that I should know? And then you would just say what that is. Can I make some sort of simple substitution and then do the integral according to a definition? If so, do that. If not, then we start learning to do integrals by some sort of intermediate technique. So integration by parts is probably the next good choice to think about. Is that the proper way to do it? When we get to something like this that looks very similar to a definition, maybe can't be done by u substitution, and integration by parts doesn't really work, it could possibly be, especially if it has something that looks similar to an inverse trig statement for a definition, that could likely be the method of trig substitution. Trig substitution, if you'll remember some Pythagorean identities, and these can be arranged a bunch of different ways, right? Here I have a few of them, the ones that we're going to focus on in this video, and the method for trig substitution is based upon a concept of creating Pythagorean identities to make the integral something that we can work after we simplify using a Pythagorean identity. So these identities that we have here are similar to something that looks like what we would see in our inverse trig antiderivatives, right? These kinds of statements, we have a squared minus u squared plus u squared, and u squared minus a squared. So these are the three forms that we will see that we may use in trig substitution. Remember that a is always something that just involves a constant, and u is something that involves your variable of integration. If you look at this first one, you may notice this looks similar to a statement for an antiderivative that becomes an inverse sine, and so we are actually going to let u equal a sine theta when we see an expression like this and need to use trig substitution. The one with plus between the squares, we're going to, because that looks similar to tangent and similar to this identity, we are going to actually let u equal a tan of theta for our substitution. And for the last one, variable term minus constant term, both squared. This looks similar to something that gives us a secant, inverse secant. So we're going to let u equal a secant theta. So if you can know these three forms and how to spot them and sort of relate them back to the definitions for integrals that you probably already know, that will tell you whether to let u equal a sine theta, a tangent theta, or a secant theta. For the three substitutions that we do, what we're doing basically is we are telling you information about an angle in a right triangle. So if u is equal to a sine theta, for example, I could divide both sides by a and solve this for sine theta. That would give me that sine theta is u over a, and we know in a right triangle that sine of theta is the opposite side over the hypotenuse. Using Pythagorean theorem, we could then solve for the third side, and then any sort of trig statement that I get as an end result for my integral, sine theta, cosine theta, tangent theta, etc., I can simply use the sides of this triangle and opposites, adjacents, and hypotenuses to then substitute back to the original variable. For the second one, if u is equal a tan theta, if we divide both sides by a, then you get tan theta is u over a, and remember tan theta is opposite over adjacent in a right triangle. You could do a similar thing and then solve for the third side of the triangle using Pythagorean theorem. For secant, similar idea, divide both sides by a. Secant would be u over a, and that's hypotenuse over adjacent in the case of secant, and then you could solve for the third side of the triangle using Pythagorean theorem there as well. So we will go ahead and construct a triangle when we work these out in our example videos to show you exactly how to relate everything in terms of theta once we finish the problem and get it back to the original variable that we were working with. For our first one here, which is our last example from the beginning of the video, integral dx over the square root of 1 plus x squared. So I notice that this is a constant squared plus a variable squared statement. In this case, my a is 1 and my u is x. So since this is a squared plus u squared, I'm going to use substitution u equals a tangent of theta. That's the one I would choose versus the sine or the secant, and the plus tells me that. If I do that, then in this case, since u is x and a is 1, then x equals tangent of theta. And if we're using this substitution to change x's into thetas, of course I'm going to need to change dx into a d theta expression as well. So I take the derivative, and dx is secant squared theta d theta. To set up my triangle and the sides in my triangle to be accurate, if I place my theta in the bottom left here, then I would think of this as a fraction, that tangent of theta is x over 1, so that I know that x is the opposite side in tangent over the adjacent side. So I would go ahead and say that this side is x, and the adjacent side here would be 1. And then solving using Pythagorean theorem, this squared plus this squared would give me this squared. You can work that out on your own if you want the details, but that actually would make this side the square root of 1 plus x squared. Now we simply substitute using these expressions for x and dx. And so if dx is secant squared theta d theta, then that becomes my numerator, secant squared theta d theta. And the bottom, I get the square root of 1 plus tangent squared theta, because I have x squared down there. Now this is the point where you should notice, once you've plugged everything in terms of theta, that you should get an expression that is a Pythagorean identity. And you'll notice our Pythagorean identity right here, 1 plus tangent squared theta, that is actually going to be the same as secant squared theta under the root. So as we do this, our next line of work here, so I'll leave the top alone, secant squared theta d theta, I get square root of secant squared theta, replacing that using Pythagorean identity. And then we simply reduce this. Now, the square root of a square is actually the absolute value of that thing, but I'm going to go ahead and make the statement, if this makes sense, that we're working in a right triangle. All of the angles are in quadrant 1, and so everything is going to be positive anyway, so we don't need to write that this is the absolute value of secant. We are simply going to say that it is secant of theta on the bottom, so we'll have secant squared theta d theta over secant theta. And then we can reduce the powers. On top here I have square of secant, I have a single copy of secant on the bottom, so I end up with the integral of secant theta d theta. And if we know the definition for the antiderivative of secant, that's going to be ln of absolute value secant theta plus tan theta, plus our constant. Okay, so we have now completed the integral. When you get to this step here, whatever you get as your final thing you're going to integrate, you're going to have to make a decision when you get there. Sometimes it'll just be a straightforward definition. Sometimes you'll have to use an identity to integrate this. Sometimes you'll have to do a u substitution. It really just depends. So you will have to make a decision once you get there each time you use trig substitution. Okay, now I need to replace my secant of theta and my tangent of theta and get everything back in terms of x. A nice thing that we already had, if you'll notice up here, tan theta was equal to x, so I already know what tangent of theta is. So this is simply going to be an x there that replaces tan theta to get us back to the original variable. To solve secant theta, we can think about in a right triangle that secant of theta is equal to the hypotenuse over the adjacent. And if we know that, then if my theta is here, hypotenuse is the square root of 1 plus x squared, and the adjacent is 1, so that means that secant theta is just going to be replaced by the square root of 1 plus x squared. Okay, so if we plug that then into our answer, we would get an answer of the ln of the absolute value of square root 1 plus x squared plus x plus our constant of integration. Okay, we actually have 9 example videos worked out for you using trig substitution. So you can see these 3 forms with a squared minus u squared statements in them. So we have 3 examples for a sine substitution. You can check out any of those going directly to them in our Calculus 2 playlist, or just simply work through each of these individually in order. We also have 3 for tangent substitution. You can see these statements have something involving a squared plus u squared in them. And we have 3 secant substitutions, variable expression squared minus constant expression squared. All right, check those out when you have a moment. We'll see you then.